We can move to the second talk, which is from an Italian from outside Italy again, as many of us. Elisa Franco, thank you for joining. And she's
Hi everyone.
and she. Can you share your screen in the
Yes,
meanwhile? So
I
and
will. Sorry, give me a second.
she's presenting a really control. Type of title because there is feedback in the title, which I like. Feedback SIR model, advantages and limitation of infection-based social distancing.
All right. Let me see.
Perfect.
Do you see my screen right now?
Yes,
Do you
we
see
see the screen, we see you.
presentation?
No, actually, no, just sharing the wrong screen, I think, because just
Okay.
this one,
Working
this
with you.
one.
Hold on.
No
Because
problem.
I was trying to do what Mario suggested to just share the
The app,
keynote,
but it
but
didn't.
that didn't work because I have two screens. Do you
Okay,
see the screen now?
this is perfect.
Okay, great. All right. So thanks for having me, and it's really nice to see all the usual suspects that I would see at CDC
Yeah.
or ACC. All right. So I'll cut through the chase. So my model is much simpler than everything you have seen so far, and it's really meant to highlight the effects of feedback on an SIR model when you consider all the. It's a population level model where you consider individuals really as particles in a large space that have interactions, and how does social distancing affect those interactions. So we start from the SIR model. I'll go quick on this because we all know how this works. So the SIR assumes you have susceptible and infected that interact at a certain rate of beta, and you get two infected out of a susceptible and infected, and then there's a certain recovery rate. We all know the definition of transmission rate constant, which is basically probability of infection given a contact and then multiplied by the average rate of contact. And we all know the definition of gamma, recovery time constant, which is the inverse of how long the infection lasts. So because these are mean field models, they assume you have a well-mixed population. So you can really think of individuals as particles in a well-mixed solution. And so you can rewrite this as a series of chemical reactions, right? You have S plus I gives you 2I, and from there you have recovered. And then you have a mass conservation law because you assume there's no birth and death, and the total population remains constant on the time scale of the epidemic. So from there, you all know how to derive the model. And then from there, you can normalize all the variables with respect to total population. You can get rid of the recovered equation, so you end up with only two. In addition, you can also rescale time and define the reproduction ratio, reproduction number as the ratio of beta over gamma. And so you get a two-dimensional model that only has one parameter, R0. Okay, and we all know that the epidemic can proceed only when the product of R0 times the susceptible population is greater than 1. Otherwise, you reach immediately the peak for infections and you go to equilibrium. And the equilibrium is the disease-free equilibrium that you know. You're all familiar with that. I just wanted to set up the introduction. Now, can we model more explicitly daily contents and probability of infection? So let's say that actually susceptibles and individuals, as if they were particles in a well-mixed solution, they can come in proximity and create some sort of complex, okay? And how long that complex stays around is going to affect how likely you are to generate an infection, okay? So you have two reactions here, rho plus and rho minus are the reaction rates, and they tell you how quickly you associate and dissociate from a complex. From there, you have, again, a certain probability of creating two infections, and then there's the usual reaction of recovery. So to put it in like a more intuitive way, you see a crowd, and if you zoom and if you focus on that particular corner over there, you see some individuals are actually moving around more quickly than others, while others are sticking together. So those rho plus and rho minus are meant to indicate how long you spend in a neighborhood of someone else, and the more you do so, the more likely you are to be infected. So if you include this reaction, you write down the dynamics of C, of the contact species, so to speak, And of course, that will equilibrate much faster than relative to the time scale of the epidemic. So you set that, you find equilibrium, and with that equilibrium, you can redefine the the transmission rate beta as a function of rho plus, rho minus, and phi. Okay, so now, what does it mean to do infection-aware social distancing? So we have this model over here, this sequence of reactions that I just described. Now, suppose that if you know that there are many infections around, you simply increase the rate at which you dissociate from other individuals. So, you might say hi to your friends, but you're not going to stay too close to them for very long. And this behavior is enforced the more infections you're aware of in that area. So as opposed to the video that I showed you before, this is what the scenario would look like. So people slide away much faster. They don't stay close to each other. So with this additional reaction, you can actually find a new equilibrium for the contact species, and you define a new parameter, kappa, over here, which depends on the rate at which you are sensitive to infected, as well as the dissociation and the probability of infection. Okay, and as you can see, this new term appears over here, which is 1 over 1 plus kappa I. And here you have another constant, which is akin to the beta that we found before. So, why is this a plausible model? Because knowledge of infection does change individual behavior, reduces the duration of contacts. Also, it encourages people to wear protective equipment. And so you reduce also the average number of contacts in addition to that. So with this, modification, you can define a new SIR model that includes infection-aware distancing in an explicit way. And I called it feedback SIR for short. And basically, the net result is that you still have R0 there, but R0 actually can be redefined to be an R of I of the number of infections, and it changes over time in a continuous way. So it's negative feedback because the more infections you have, the lower R of I will be. And I should mention that similar models have been proposed and considered before. This is very similar to the well-known Michaelis-Menten approximation in chemical kinetics, this type of term. And so, for example, the famous paper by Bootsman Ferguson in PNAS 2007, this is the paper where they looked at influenza epidemic in the US. They did include a term like this when they were fitting their model, but they were actually doing feedback on the death awareness. And it was more meant to model the government interventions. And then there's a series of other works where they included Michaelis-Menten type terms like this for modeling awareness of infections that would improve the rate of vaccinations, and also in terms of modeling the information spread. But I'm not aware of any analysis on this particular simple two-variable model that would pay attention to how specifically the feedback affects the outcome of the dynamics. So with this continuum approximation, again, this is a continuum approximation of the effects of social distancing on R0. And as you can see, this R of I is a monotonically decreasing function of the infection levels. And here is a plot that shows you how it changes the larger this function kappa. And now let's look at the solution of the SIR model in this case. So we are all very familiar with the picture of flattening the curve, okay? So you see simulations where they compare with an SIR model with a high beta is compared to one that has a low beta, and what the simulation shows is that the peak of infections is substantially delayed. It's lower, but it's also substantially delayed, and I think that this is somewhat misleading and also probably demoralizing to people, to the public, because it gives you the idea that the peak is never going to come and it's going to be really late. Where in truth, if you do have infection awareness type feedback, the peak is not delayed because beta is actually time varying. So this is a result of simulations where you include infection aware distancing and for different values of kappa, okay? And I picked as nominal values R0 of 2.5, which is reasonable for many of the, it's been fitted for many infections around the world, and it's a reasonable number. So what you see if you look at the curve of infections is that the peak is not significantly delayed, but of course you have a much slower convergence to equilibrium. So the duration of the infection is much longer, depending of course on the parameters you take. Let's look at the reproduction number. That is time varying. So it's not a constant reproduction number. It depends on the number of infections, and the larger kappa, so darker here means kappa equals 0, so the nominal case. And then for increasing kappa, you go down. As you see, it goes down up to like a little bit above 1 in this case, because I only limited kappa from 0 to 10. So social distancing changes a function of infections, and a large kappa means that social distancing happens sooner and you have a more drastic decrease in R. Now, the peak is, sorry, this is the wrong plot. I'm going to skip this slide. Let's go on. So there can be delays, of course, in the infection information, but that has a moderate influence on the dynamics. So, for example, here you see a solution where I have implemented a delay in the feedback term. And up to 14 days, you can still see a decent flattening of the peak. This is for kappa equal to 2. Now, if you compare that to the case with no delay, you can see that there's a relative increase in the peak of about 30% for two-week delay. And the relative infection duration stays roughly flat. It doesn't change that very much. So now the next question is, can this model capture the trends of current COVID infection data? The answer is it can in some cases, but remember this model has only 2 parameters, R0 and kappa, and 3 if you look at the dimensional form. And of course, the more parameters you add, the better you can fit, but this is not the purpose of this exercise. The purpose here is to develop a continuum approximation of infection distancing, and also identify and illustrate challenges, okay, with a simple model. So the data source for the data I'm going to show you now is obviously the Johns Hopkins repository. And so let's start with Spain. So for Spain, we get a fit. First of all, the data are circles here, and I'm plotting active infections, and deaths and recoveries. The active infections in red, deaths and recoveries in gray. The dashed lines are simulations. So the fit for kappa here is about 2,000. So this means that basically the feedback started kicking in when the population was inversely proportional to this value of kappa. So it was about 1/2,000 level of infections. This was fitted to the normalized model, of course. So you have to consider these numbers as, this is inversely proportional to the fraction of current infections. So the fit shows that Spain started with an R0 that was really high, and then over time it decreased. The fit is decent in my opinion, although it kind of departs from death and recoveries toward the end. But I am not actually sure that recoveries and deaths are reported accurately for any of the countries, in particular recoveries for people who are not very ill and are not at the hospital. It might not be possible to actually track them. For Italy, we have a similar situation. Kappa is also around 2,000. R0 is slightly slower in my fit than Spain, but the fit is, does a decent job at capturing the situation. And I can show you more of these plots. For example, for the UK, UK seems to have started with a lower R0, if you trust this model, but also a much lower kappa. And again, the fit for deaths and recoveries is not good. I also penalized in my fitting function the active infections much more than deaths and recoveries. Let's look at the United States. We also have a pretty low kappa that is actually lower than what measured for Italy, which indicates that basically they started distancing a little bit later when the number of infections was higher. The model does not do a good job with Germany, and I'm not exactly sure why. I haven't found an explanation. There could be issues with the model itself. It's not able to capture the way they are doing social distancing. but it could also be that their particular situation is different. So the notable thing is, though, that the kappa fit is much higher than in any other case, which suggests that as the epidemic has evolved, has shown that Germany seems to have been able to contain faster and better than everybody else. Now, I want to conclude with a slide. I'm not in the business of making predictions with this model because it's really an illustrative scenario. But if we were to trust it, if we were to continue to do social distancing just based on information of infections, what would things look like in the future? And it's, it doesn't look that great because the number of infections is actually staying pretty much constant for a really long time. Okay, so we're close to reaching the peak, but then it doesn't look like we're going to get any better if we don't enact stronger measures. And same for Italy. So it looks like this plateau could be maintained for probably a couple of years if we don't do anything, if there's no vaccine. Of course, this is a kind of like a grim scenario. And if we look at the R0 that is predicted in these cases, the R of T, sorry, it's kind of staying close to 1 at all times, but never really going below it. So, there's probably risks in trying to follow an approach that is solely based on infection information that is average. So to conclude, I know already I'm a couple of minutes over. So I propose a continuum approximation to modeling social distancing based on information on infections. The model only has 2 parameters. And like one advantage of infection-based distancing is that it's an easily justifiable policy because you have, assuming that of course you have good information about infections and there's ability to distribute that information. The disadvantage is that you have an extremely slow convergence to disease-free equilibrium. And I have a few conjectures about structural properties of this model, but it's all in progress, so I'm not discussing them today. So with that, I conclude, and thank you for your attention.
Thank you very much, Elisa. Thank you. We have to work on this applause. So thanks, Elisa. Thanks a lot. Okay, muted. I'm muted. Okay, now I'm unmuted. So it seems that we've seen different models, but the message is really clear from all models that we have to be very careful. And Martina, do we have questions?
We have a question from Giuseppe Calafiore.
Okay. Beppe?
Yes.
Giuseppe, please go ahead.
Yes, just a simple question. Elisa, how do you estimate or assume the initial value for the susceptible population?
So in the data I showed, I threshold the data. So I discard data that are below, I think, two infections per million. And so I use that as an initial condition.
No, but the susceptible, I mean, what is the initial population? All the population? The total
that's all normalized to the total population of the country.
Okay.
For the susceptible, I just take the total minus the infected, yes.
Okay, so all of it, yes.
All of it.
Yeah.
Okay, thank you.
Thank you. So, other questions? I think Francesco had a question.
Yes, we have another question from Francesco.
Yeah, I was trying to understand if your model is somewhat equivalent to proportional control or inversely proportional control, I'm not sure, of the beta parameter based on the number of infectious people, with kappa somehow playing the role of proportional gain, or do I miss it?
So these type of models are adopted all over the place in biology, and some people would argue that this is a proportional controller, but we can talk about that offline.
Okay. Okay. So thank you, Elisa, again. Thank you, Elisa, and